Hello, I am Professor Bodziak, and I will be teaching coding today for the students. We're going to start off by talking about ASCII computer code. Now, computers use binary code. Information is coded in ones and zeros. Each one or zero is called a bit. So, make this point stressed. A bit, a 1 or a 0 is called a bit in binary code. In the early years of computer development, different companies applied the binary system. The code for the letters for every word would be different according to the company which was coding that particular word. But soon a set of standards were developed, and computer manufacturers agreed to use one standard code. It's called ASCII code, ASCII. It stands for American Standard Code for Information Interchange. It's an 8-bit code. So ASCII code is 8-bit code. So each of the letters on your keyboard are represented by 8 bits, where a bit is either a 1 or a 0. So those, so every key on your keyboard, be it a letter, a lowercase letter, an uppercase letter, or a punctuation mark, it's going to be represented by its own particular 8 bits. 8 bits in computer language is called a byte. That's spelled B-Y-T-E. Binary codes with 8 digits can be stored in 1 byte of computer memory. Okay, so to further understand how this is used and why it's used, we're used to writing numbers in decimal. Okay, so let's say I write the number 123. Each position in this decimal number has a particular value for the number that you place in it. The decimal system has 10 different digits in it. That's why it's called deca means 10 in Greek. Okay, so you've got the digits 0 through 9. Okay, so when you write a number in the decimal system, you could also write 123 with a small 10 here, meaning that's a base 10 number. Okay, so the first position has whatever digit you put in it multiplied by 10 raised to the 0. Okay, any number raised to the 0th power is equal to 1. So this is 3 times 10 to the 0 plus 2 times 10 to the 1 plus 1 times 10 to the 2. Okay, 3 times 10 to the 0 is equal to 3. 2 times 10 to the 1 is equal to 20. 1 times 10 to the 2 power is equal to 100. Add these up and you get 123. That's why this number is of significance to us in this respect in the decimal system. Now, similarly, computers are built of electronic components, and one of the main components is transistors. All right, a transistor is a small electrical component. So basically, transistors are either saturated or unsaturated. Think of it as either off or on. That's why ones or zeros are of great importance. That composes the language that computers basically work in. Binary. Bi means 2. So we use binary arithmetic when we talk about computer languages. So if we have several different spaces to enter a number in binary, the first space represents 2 to the 0th, the second 2 to the 1th power, the third 2 to the 2 power, the fourth 2 to the 3 power, the fifth 2 to the 4th power. Okay? So, since it's binary, bi means 2, there are only 2 possible digits that can be used, a 0 and a 1. So, you can only put either a 0 or a 1 into each position. So, if I write the number 1 here, like this, 0, 1, that's 1 times 2 to the 0, okay? Any number raised to the 0th power is equal to 1. That's 1 times 1, which equals 1. So that is just a 1 in binary. If I write 1, 0, that's 0 times 2 to the 0 plus 1 times 2 to the 1, okay? So 0 times 1 is 0. 1 times 2 is 2. So that is the representation of a 2 in the binary number system. Okay? If I write 1, 0, 0, that's 1 times 2 to the 2 plus 0 times 2 to the 1 plus 0 times 2 to the 0th. Okay? 0 times 2 to the 0th is 0. 0 times 2 to the 1 is 0. 1 times 2 to the 2 is 4. So this is the representation of the number 4 in binary. So that explains what each of the positions mean when you write a number in the binary system. Okay? So it consists of only zeros and ones, and those zeros and ones each have their own special value depending upon where they are positioned in the number. So, as I've described, that's the 2 to the 0th place, the 2 to the 1th place, the 2 to the 2th place, the 2 to the 3rd place, the 2 to the 4th place. Now, converting that back into decimal, 2 to the 0, okay, any number raised to a 0 is a 1. 2 to the 1 is a 2. 2 to the 2 is a 4. 2 to the 3 is equal to an 8. 2 raised to the 4th power is equal to a 16. 2 raised to the 5th power equals 32. Okay, so a 1 in this position gives you a 4 in your number. A 1 in this position gives you an 8 in your number. A 1 in this position gives you a 16 in your number. So for example, 1, 1, 0, 1, 0 would equal 16 plus 8 plus 2, which equals 26. Oop. Yep, 26. So, that's the basics. Okay, now, as we discussed the ASCII system, American Standard Code for Information Interchange, it gives a binary number for each letter represented on your keyboard. So this chart is a chart that you have and would be of importance to you for the things that we're discussing. And it's showing you that a blank space is a 32, represented by binary number 001, 00000. So that's basically 2 to the 5th. Exclamation point is a 33, represented by 00100001. So it's basically 2 to the 5th, 32 plus a 1. Here's the double quotes, represented by 00100010. Okay, so that's a 2 to the 5th plus a 2 to the 2. So that's 1 times 2 to the 1 plus a 2 to the 5th. That's 32 plus 2, which is equal to 34. Continuing along with that line of reasoning, here's the binary number that corresponds to each code for every character. Here's the capital A, 01000001, which turns out being a 65 in decimal. Here's a capital D, 0, 1, 0, 0, 0, 1, 0, 0, which turns out being a 68 in decimal. Here are the lowercase numbers and letters. Here is a little a. It turns out being 0, 1, 1, 0, 0, 0, 0, 1. That ends up being a 97 in decimal. Here's a lowercase b. Ends up being 0, 1, 1, 0, 0, 0, 1, 0. Ends up being a 98 in decimal. When you take that binary number and you convert that back the same way as I described here, knowing that each value to the left is you increase the exponent by 1 for the representation of a 1 in that position. That is how the decimal numbers on this chart were derived. Okay, so you can see that starting off at capital A at being a 65, we can go all the way down to capital Z, which is a 90 in decimal, and here's its binary equivalent. Here's the little a in character in binary, which is a 97 in decimal, and it goes all the way down to a small z. Lowercase z is 122 in decimal. Okay, so our example on this page asks us to do an activity. We want to use the ASCII code to write our first name or our nickname in binary numbers, beginning with an uppercase letter and continuing with lowercase letters. Put the letters of your name in the first column. So we can write in this column using this chart. Now, if you look at the bottom of page 2, you will see activities listed. This activity says, use the ASCII code to write your first name or nickname in binary numbers, beginning with an uppercase letter and continuing with lowercase letters. Put the letters of your name in the first column. That's an activity that I would like you to do. Okay, and to show you how to do it, I will try an attempt at doing it. Let's say your first name was Dennis, Dennis. So by following these regulations, this rule here, I would start with a capital D, which is a 68 in decimal, and it corresponds to being 0, 1, 0, 0, 0, 1, 0, 0. Okay, the next letter will be a little d, a little e rather. If you look at a little e, it is a 101 in decimal, which corresponds to the binary number 0, 1, 1, 0, 0, 1, 0, 1. Next letter is an N, little lowercase n, corresponds to 1, 1, so it's 110 in decimal, which in binary would be 0, 1, 1, 0, 1, 1, 1, 0. Next letter is another N, so it's the same binary number, 0, 1, 1, 0, 1, 1, 1, 0. Next letter is a small case I. That would be a 105 in decimal, which is the equivalent of a 0, 1, 1, 0. One, 0, 0, 1. Next letter is a little lowercase s. In decimal, that's a 115. In binary, that's 0, 1, 1, 1. 0, 0, 1, 1. Okay, so we've done the first activity here. We use the ASCII code to write a first name or nickname in binary numbers beginning with an uppercase letter and continuing with lowercase letters. This requests that you put the letters of your name in the first column. So basically what I've written here on this paper can be printed by you in this column here, whereupon you put the binary digits in these spaces. Okay? The next activity says, on a separate sheet of paper, write a short message in ASCII. Exchange messages with a partner and decode each other's message. So first write the message in English. Okay, the message might be, hello, how are you, my friend? Followed by a question mark. Convert that to ASCII. H, capital. That's a 72 in decimal, which corresponds to 01001. Next is a little lowercase e. That's a 101 in decimal, corresponds to a 0, 110, 0101. The next letter is a lowercase l. That's a 108 in decimal. Binary, that's 0, 110, 1100. The next letter would be another lowercase l. Same number, 0, 110, 1100. Next would be a comma. And actually this chart is not giving us a comma. So this chart is missing a little bit. We will eliminate the comma from our original message. Instead, we will merely put in a blank space. A blank space is a 32. Which is 0010, 0000. Okay, we must put this O here. And that's a small case O. 111 in decimal, the equivalent in binary is 0, 110, 1111. Okay, now the next letter is a capital H for how. We've used that already. 0, 1, 0, 0, 1, 0, 0, 0. Next is the lowercase o. We've already found that. It's 0, 1, 1, 0, 1, 1, 1, 1. Next is a lowercase w. Here's the W, 119, 0, 1, 1, 1. 0, 1, 1, 1. Next is a space. We found the space to be a 0, 0, 1, 0, 0, 0, 0, 0. Next is a small a in the R word. R is a 97 in decimal. It's a 0, 1, 1, 0. 0001. Next would be the letter R, small case. 114 decimal corresponds to a 0, 111, 00, 10. Next, lowercase e, 101 in decimal corresponds to a 0, 110, 0101. Next is the space, and we already found that to be 0010, 0000. Next will be lowercase y, which is a 121 in decimal, corresponds to a 0, 111, 1001. Next, lowercase o, which we already found right here. 0, 110, 1111. Next, lowercase u. We found that here. 117 corresponds to a 0, 111, 0101. Next is a space. We found that here already. 0010, 0000. Next is the little m, lowercase m in my. That is a 109 in decimal, which corresponds to a 0110. 1101. Next, lowercase y. We already found that to be 0111, 1001. Next, a space. We found that to be a 0010, 0000. There's the space. Next, lowercase f. A 102 in decimal corresponds to a 0110, 0110. Next, lowercase r. It's a 114 in decimal, corresponds to a 0111, 0010. Next, lowercase I. That's a 105 in decimal, corresponds to a 0110, 1001. Next, lowercase e. We already found that right here. 0110, 0101. Next, lowercase n. Looking on the table, we have n is 110 in decimal. Corresponds to 0110, 1110. Next, lowercase d corresponds to a 100 in decimal. In binary, that's 0110. Zero, 1, 0, 0. Okay, so in order to solve this activity, okay, we wrote a short message we wrote it in English, and then we used this table to convert the English into each letter being its ASCII representation. And we talked earlier, the ASCII is a code consisting of 8 bits. Okay, and we talked why a bit is of importance with computers due to the electronics of the transistors and so forth, and it's basically either on or off, a 1 or a 0 when we write these numbers. Okay, let us look at the next activity. The ASCII code for a blank space is the decimal number 32, which is a binary 00100000, and the little 2 means base 2. Why do you think it is important to have a code for a blank space? Well, when the computer prints out text message, any kind of text, right? Text often has blank spaces in it to separate characters, to separate words from each other, so we can identify one word from the next word adjacent to it. So we have to have blank spaces being recognized as this text is being printed out, or else it would not be a complete word. The words would all be right next to each other, and we wouldn't be able to read it. They would not be English words. We need spaces to separate words so we can identify individual words. That would be a good answer to such a question. How many characters of text are there in an average book? That might be a good question for you to look up and examine. I would estimate myself that there must be thousands, probably several tens of thousands of characters. Maybe 20, 30,000 characters, maybe more, depending upon how long the book. So to help answer this question, select several different books of different lengths. For each book, estimate the number of characters of text. Count the punctuation marks, include the blank characters between the words and sentences. So once again, these punctuation marks are characters that the computer is printing out, so each must have its own representation, or else those characters wouldn't get printed. As this goes with the spaces between words, we must have a representation of a space, or else words would be next to each other, and we would not be able to. They would not be proper English words, and we wouldn't be able to read it. Okay, so since ASCII is an 8-bit code and requires 8 binary numbers to represent each letter, blank space, or punctuation mark, how many binary numbers does it take to represent the text of an average book? Basically, we take a guess at how many letters there are, and we multiply it by 8. So if we took a guess at 30,000 letters, we would multiply that by 8 to be 240,000 binary numbers of ones and zeros. So we're multiplying 8 by the number of characters in the text because it takes the eight of these digits to represent each character that's in the book. Now you should have this worksheet. Use an ASCII table to decode the following message. Okay, so it gives us 83. Let us decode this message. First character is a decimal 83. This is the table that you would use to solve the problem. We look at 83, it's a capital S. Next is a 116. Look at our table. 116 is a little t, which is a capital S. We got a 116, which is a little t, and you can see that 116 right here. Here we have a 101. A 101 is a little e. Here we have a 119. A 119 corresponds right here to a little w. Here we have a 97. A 97 corresponds to a little a. Here we have a 114. 114 corresponds to a little r. Here we have a 116. 116 corresponds to a little t. Here we have a 32, which is a space. First word is Stewart, and we got a space here. Next is a 116. The 116 is a little t. Next is a 104. 104 is a little h. Next is a 101. 101 corresponds to, on our chart, to a little e. Next is a 32, corresponds to a space on our chart. Next is a 99, corresponds to a little c on our chart. Next is a 111, corresponds to a little o on our chart. Another 111, little o. Next is a 108. It's a little l. Next is a 101. A little e. Next is a 115, as you can see. 115 is a little s. Next is a 116, which is a little t. Next is a 33, which is an exclamation point. So there's our message, Stewart the coolest. Okay, and so for your assignment, do the rest of these. Encode your first and last name in ASCII, convert these numbers to decimal, then use the ASCII table to determine the letters they represent. So we talked about how to do that conversion. We talked about how to do this conversion. Okay, you're going to convert each of these numbers to decimal. Each of those spaces corresponds to a representation of 2 raised to an exponent, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so forth. Calculate those out and then add those numbers up in decimal. Okay? Go to the ASCII table and determine the letters they represent. So they've given us 1, 2, 3, 4 numbers there. Next, they want us to decode these values. ASCII code 78, convert it to a binary value. Okay? So, by knowing what I've already described, 2 raised to each of these powers, that provides its representation. A 2 to the 0 for the first column, a 2 to the 1 in the second column, a 2 to the 2 in the third column, a 2 to the 3 in the third column, and so forth. So a binary representation, as we have described, figure out which one corresponds to a 78. And this one's like the inverse. Do what we just talked about, add up each of those decimal numbers, and then you will come up with the total decimal number, which you can then use to look onto to this table and determine which letter corresponds to that. So basically all of these are the same kind of, it's either one or the other type of conversion, ASCII to binary or binary to ASCII. We've got another, number 5, where it asks us to write a secret message. Using this ASCII chart right here, we will look up the decimal values for each letter and write it down in a series. So, similar to what we just did, write your message in English and then go to this chart and determine the corresponding numbers for each of these in decimal value, and then just write those corresponding numbers down. Don't forget to have spaces between the letters that require them. Between words, you're going to need spaces. So we've talked about how to convert decimal to binary. Record your encoded message in 8-bit groups of bytes on a separate piece of paper, 1 byte per line. Okay, so each byte is a character shown by this chart. So each of those bytes corresponds to each of these characters, and the characters put together correspond to the words in your message. Give this encoded message to a friend and have them decode it. Okay, so that should pretty much keep you busy. All right, thank you. So as we discussed earlier at the start of the course, either enter into the chat or into the comment section of the YouTube clip if you're watching me in YouTube. How many bits in a byte? Okay, thank you.